Welcome to this comprehensive guide on sine product to cosine identities. These powerful mathematical tools allow us to transform products of trigonometric functions into much simpler sums or differences. Product to sum identities are mathematical formulas that convert the product of two trigonometric functions into a sum or difference of trigonometric functions. For example, the product of sine A times cosine B can be rewritten as 1/2 times the sum of sine of A plus B and sine of A minus B. These identities are incredibly valuable for three main reasons. First, they help us simplify complex trigonometric expressions that would otherwise be difficult to work with. Second, they're essential for solving trigonometric equations that appear impossible at first glance. Third, they're crucial tools in calculus, especially for integrating products of trigonometric functions. Throughout this video series, you'll master the four main product-to-sum identities. We'll walk through step-by-step derivations so you understand not just how to use them, but why they work. You'll see practical examples that build your problem-solving skills and discover real-world applications in science and engineering. By the end, you'll have the confidence to tackle any trigonometric expression involving products of sine and cosine functions. Are you ready to transform your understanding of trigonometry? In the next section, we'll dive deep into the fundamental concepts behind these powerful identities. You'll see exactly how products become sums and why this transformation is so useful in mathematics. Before we dive into the specific product-to-sum identities, we need to understand what trigonometric identities are and why they're so powerful in mathematics. A trigonometric identity is an equality involving trigonometric functions that holds true for all values of the variables for which both sides of the equality are defined. For example, the Pythagorean identity sine squared x plus cosine squared x equals 1 is true for any value of x. This is what makes it an identity rather than just an equation. Product-to-sum identities are special trigonometric identities that rewrite the product of sines and cosines as a sum or difference of trigonometric functions. The basic idea is simple. We take a product of trigonometric functions and transform it into a sum. This might seem like we're making things more complicated, but it actually makes many calculations much easier. These identities are incredibly useful for several reasons. First, they help simplify complex trigonometric expressions that would otherwise be difficult to work with. Second, they make solving trigonometric equations much easier by converting products into sums, which are often simpler to manipulate. Third, they're essential in calculus, particularly for integration techniques when you need to integrate products of trigonometric functions. Finally, these identities appear frequently in physics and engineering, especially when analyzing wave phenomena, signal processing, and oscillatory systems. The key insight behind product-to-sum identities is that products of trigonometric functions are often much harder to work with than sums. These identities give us a systematic way to convert between these two forms, choosing whichever is more convenient for our particular problem. Now that we understand what trigonometric identities are and why product-to-sum identities are useful, we're ready to explore the four main product-to-sum identities that form the foundation of this powerful technique. Now we'll examine the four main product-to-sum identities. These powerful tools allow us to transform products of sine and cosine functions into sums or differences, which often makes complex trigonometric expressions much easier to work with. The first identity handles the product of two sine functions. When we multiply sine of alpha times sine of beta, we get 1/2 times the difference of two cosine terms, cosine of alpha minus beta minus cosine of alpha plus beta. The second identity deals with the product of two cosine functions. Cosine of alpha times cosine of beta equals 1/2 times the sum of two cosine terms, cosine of alpha minus beta plus cosine of alpha plus beta. Notice this is very similar to the first identity, but we have a plus sign instead of minus. The third identity transforms the product of sine and cosine. Sine of alpha times cosine of beta becomes 1/2 times the sum of two sine terms, sine of alpha plus beta plus sine of alpha minus beta. Here we're working with sine functions on the right side instead of cosine. The fourth and final identity handles cosine times sine. Cosine of alpha times sine of beta equals 1/2 times the difference of two sine terms. Sine of alpha plus beta minus sine of alpha minus beta. This is similar to identity 3, but with a minus sign between the terms. Before we move on, notice these important patterns that will help you remember and apply these identities. First, all four identities have the factor 1/2 in front. Second, they all involve alpha plus beta and alpha minus beta combinations. Third, when you multiply two functions of the same type, sine times sine or cosine times cosine, the result involves cosine functions. But when you multiply different types, sine times cosine, the result involves sine functions. Finally, and this is crucial, pay very close attention to the signs. The first identity has a minus sign, the second has a plus sign, the third has a plus sign, and the fourth has a minus sign. Getting these signs wrong is the most common mistake students make. These four identities are your toolkit for converting products into sums. In the next sections, we'll see exactly how to apply them to solve real problems. The key is recognizing which functions you're multiplying together, then selecting the appropriate identity and being careful with the signs. Now that we've seen all four identities and their patterns, we're ready to learn how these powerful tools are derived from the fundamental sum and difference formulas. Now we'll discover how the product to sum identities are actually derived. Understanding these derivations will help you remember the formulas and see the beautiful connections between trigonometric concepts. We begin with the fundamental sum and difference formulas for sine and cosine. These are the building blocks we'll use to create our product to sum identities. Let's derive our first product to sum identity. We want to find a formula for sine alpha times cosine beta. We'll add the sum and difference formulas for sine. Now we add these two equations together. Notice what happens when we add the right sides. The cosine alpha sine beta terms will cancel out. Finally, we solve for sine alpha cosine beta by dividing both sides by 2. This gives us our first product to sum identity. Now let's derive the identity for cosine alpha sine beta. This time we'll subtract the sine difference formula from the sine sum formula. When we subtract, the sine alpha cosine beta terms cancel out, leaving us with twice the cosine alpha sine beta term. For cosine alpha cosine beta, we use the cosine sum and difference formulas. We'll add them together to eliminate the sine terms. Adding these equations cancels the sine alpha sine beta terms, giving us twice the cosine alpha cosine beta term. The fourth identity for sine alpha sine beta follows the same pattern. We subtract the cosine sum from the cosine difference formula. The key insight is that all these identities come from the fundamental sum and difference formulas through simple addition and subtraction. Now we'll work through our first example to see how product to sum identities can simplify trigonometric expressions. This example will demonstrate the practical application of these powerful identities. Our problem is to express the product cos of 3x times cos of 5x as a sum or difference. This is exactly the type of problem where product to sum identities are most useful. We'll use the cosine-cosine product to sum identity. This identity states that cosine alpha times cosine beta equals 1/2 times the sum of cosine of alpha minus beta plus cosine of alpha plus beta. Now let's apply this identity step by step. First, we need to identify our alpha and beta values from the original expression. Step 1. We identify alpha and beta from our expression. In cos of 3x times cos of 5x, we have alpha equals 3x and beta equals 5x. Step 2. Now we substitute these values into our product to sum identity. We substitute alpha equals 3x and beta equals 5x into our identity. This gives us cos of 3x times cos of 5x equals 1/2 times the quantity cos of 3x minus 5x plus cos of 3x plus 5x. Step 3. Now we simplify the arguments inside the cosine functions. Let's simplify the arguments step by step. First, 3x minus 5x equals negative 2x. Second, 3x plus 5x equals 8x. So our expression becomes 1/2 times cos of negative 2x plus cos of 8x. Step 4. We can simplify further using the fact that cosine is an even function. Since cosine is an even function, cos of negative x equals cos of x. Therefore, cos of negative 2x equals cos of 2x. Our final answer is 1/2 times the quantity cos of 2x plus cos of 8x. This is our final answer. We have successfully converted the product cos of 3x times cos of 5x into the sum 1/2 times cos of 2x plus cos of 8x. This example demonstrates how product-to-sum identities can transform complex trigonometric products into simpler sums. This technique is particularly useful in calculus for integration and in solving trigonometric equations. Product-to-sum identities become powerful tools when solving trigonometric equations. Many equations that seem impossible to solve directly become manageable when we transform products into sums. These identities help us in three key ways. First, they transform products into sums or differences. Second, they allow us to isolate trigonometric functions more easily. Third, they convert complex equations into simpler, more manageable forms. Our first example demonstrates the basic application. We need to solve the equation sine of x times cosine of x equals 1/4. Notice we have a product of sine and cosine. This is exactly where our product-to-sum identity becomes useful. We use the identity sine of alpha times cosine of beta equals 1/2 times the sum of sine of alpha plus beta and sine of alpha minus beta. Since both alpha and beta equal x, we substitute to get sine of x times cosine of x equals 1/2 times the sum of sine of x plus x and sine of x minus x. Simplifying the arguments, x plus x becomes 2x, and x minus x becomes 0. Since sine of 0 equals 0, we get sine of x times cosine of x equals 1/2 sine of 2x. Now our original equation becomes 1/2 sine of 2x equals 1/4. Multiplying both sides by 2, we get sine of 2x equals 1/2. Since sine of 2x equals 1/2, we have 2x equals pi over 6 plus 2 pi k, or 2x equals 5 pi over 6 plus 2 pi k. Dividing by 2 gives us our final solutions. Our second example involves multiple products. We need to solve cosine of 3x times sine of 2x equals sine of x times cosine of 4x. We have products on both sides of the equation. We'll need to apply product-to-sum identities to both sides. We need two identities. For cosine times sine, we use the first identity. For sine times cosine, we use the second identity. Applying the first identity to the left side, cosine of 3x times sine of 2x becomes 1/2 times the difference of sine of 5x and sine of x. Applying the second identity to the right side, sine of x times cosine of 4x becomes 1/2 times the sum of sine of 5x and sine of negative 3x. Since sine of negative 3x equals negative sine of 3x, the right side becomes 1/2 times the difference of sine of 5x and sine of 3x. Our equation now becomes 1/2 times the difference of sine 5x and sine x equals 1/2 times the difference of sine 5x and sine 3x. Multiplying both sides by 2, we get sine of 5x minus sine of x equals sine of 5x minus sine of 3x. The sine of 5x terms cancel, leaving us with negative sine of x equals negative sine of 3x, which simplifies to sine of x equals sine of 3x. Our final example is more complex. 2 sine of 2x times cosine of 3x plus cosine of x times sine of 4x equals 1. We transform each product separately. The first product becomes 1/2 times sine of 5x minus sine of x. The second product becomes 1/2 times sine of 5x minus sine of 3x. Substituting back into our original equation, we get this expression. Simplifying the coefficient, 2 times 1/2 equals 1. So we have this simplified form. Expanding the terms, we get sine of 5x minus sine of x plus 1/2 sine of 5x minus 1/2 sine of 3x equals 1. Combining like terms, sine of 5x plus 1/2 sine of 5x equals 3/2 sine of 5x. This gives us our final transformed equation. To summarize our strategy, first, identify products of trigonometric functions. Second, apply the appropriate product-to-sum identities. Third, simplify the resulting sums or differences. Finally, solve the transformed equation using standard trigonometric methods. This approach transforms seemingly impossible equations into manageable problems. Product-to-sum identities become incredibly powerful tools when we move into calculus, particularly for integration. When you encounter integrals involving products of trigonometric functions, these identities can transform a difficult problem into something much more manageable. The fundamental challenge is this. Integrating a product of trigonometric functions is often much more difficult than integrating a sum or difference. Product-to-sum identities convert these challenging products into simpler sums that we can integrate using basic techniques. The key insight is that sums and differences of trigonometric functions have straightforward antiderivatives, while products often require more advanced techniques like integration by parts or substitution. By converting products to sums, we can use the basic integration formulas we already know. Now let's work through our first example. We want to integrate the product sine of x times cosine of x. This is a perfect opportunity to use the product to sum identity for sine times cosine. First, we need to identify which product to sum identity to use. Since we have sine times cosine, we use the identity sine of alpha times cosine of beta equals 1/2 times the sum of sine of alpha plus beta and sine of alpha minus beta. In our case, both alpha and beta equal x, so we substitute to get sine of x times cosine of x equals 1/2 times the quantity sine of x plus sine of x minus x. Simplifying the arguments, x plus x equals 2x and x minus x equals 0. Since sine of 0 equals 0, our expression becomes 1/2 times sine of 2x. Now we can integrate this much simpler expression. The integral of 1/2 sine of 2x dx equals 1/2 times the integral of sine of 2x dx. Using our basic integration formula, the integral of sine of 2x dx is negative 1/2 cosine of 2x plus c. Therefore, our final answer is negative 1/4 cosine of 2x plus c. For our second example, we'll tackle a more challenging integral involving different arguments. We want to integrate sine of 3x times cosine of 5x dx. This requires careful application of the product to sum identity. We use the same identity, but now alpha equals 3x and beta equals 5x. Substituting into our identity, sine of 3x times cosine of 5x equals 1/2 times the quantity sine of 3x plus 5x plus sine of 3x minus 5x. Simplifying the arguments, 3x plus 5x equals 8x, and 3x minus 5x equals negative 2x. So our expression becomes 1/2 times the quantity sine of 8x plus sine of negative 2x. Since sine is an odd function, sine of negative 2x equals negative sine of 2x. Therefore, our expression becomes 1/2 times the quantity sine of 8x minus sine of 2x. Now we can integrate term by term. The integral becomes 1/2 times the integral of sine of 8x minus sine of 2x dx, which equals 1/2 times the quantity integral of sine of 8x dx minus integral of sine of 2x dx. Applying our basic integration formulas, the integral of sine of 8x dx equals negative 1/8 cosine of 8x, and the integral of sine of 2x dx equals negative 1/2 cosine of 2x. Putting it all together, we get our final answer. For our final and most challenging example, we'll integrate cosine squared of x times sine squared of x. This requires using multiple product to sum identities and demonstrates the full power of this technique. First, we need to use the double angle identities to express the squares in terms of cosines. Cosine squared of x equals 1 plus cosine of 2x all over 2, and sine squared of x equals 1 minus cosine of 2x all over 2. Substituting these identities into our integral, we get the integral of 1 plus cosine of 2x over 2 times 1 minus cosine of 2x over 2 dx. This equals 1/4 times the integral of the product 1 plus cosine of 2x times 1 minus cosine of 2x dx. The product in the parentheses is a difference of squares pattern. 1 plus cosine of 2x times 1 minus cosine of 2x equals 1 squared minus cosine squared of 2x, which equals 1 minus cosine squared of 2x. Now we use the Pythagorean identity, 1 minus cosine squared of 2x equals sine squared of 2x. So our integral becomes 1/4 times the integral of sine squared of 2x dx. We need to apply the double angle identity again for sine squared of 2x. Sine squared of 2x equals 1 minus cosine of 4x all over 2. Substituting this gives us 1/4 times the integral of 1 minus cosine of 4x over 2 dx. Finally, we can integrate term by term. The integral of 1 dx equals x, and the integral of cosine of 4x dx equals 1/4 sine of 4x. Putting it all together, our final answer is 1/8 times x minus 1/4 sine of 4x plus c. These examples demonstrate the incredible power of product-to-sum identities in calculus. By converting products of trigonometric functions into sums, we transform complex integration problems into manageable ones using basic techniques. This approach is essential for success in calculus and appears frequently in advanced mathematics and engineering applications. Now that we've mastered the mathematical foundations of sine product to cosine identities, it's time to explore how these powerful tools are used in the real world. These identities aren't just abstract mathematical concepts. They're essential tools in physics, engineering, and technology. One of the most important applications is in wave interference. When two sound waves or light waves meet, they combine according to the principles of superposition. The product to sum identities help us analyze exactly how these waves interact. When these waves combine, we get a product, sine of 3t times sine of 5t. Using our product to sum identity, we can rewrite this as a sum of cosines, which reveals the interference pattern. In signal processing and telecommunications, these identities are crucial for analyzing and manipulating radio signals, audio processing, and digital communications. Engineers use them to filter signals, reduce noise, and compress data efficiently. Before we conclude, let's review the four main product-to-sum identities that we've explored throughout this video. These are the fundamental tools that make all these applications possible. These product-to-sum identities are truly powerful mathematical tools with applications spanning from pure mathematics to cutting-edge technology. They help us understand wave behavior, process digital signals, solve complex equations, and even compress the music you listen to every day. To truly master these identities, practice is essential. Work through problems, apply them to real situations, and don't be afraid to experiment. The more you use them, the more intuitive they'll become. Remember, mathematics is not just about memorizing formulas. It's about understanding the beautiful patterns that govern our world.